NASA looks at going to the moon one day and to Mars, and to get to Mars they're going nuclear. The vastness of space between the stars is enough to make your mind explode. Consider the Voyager 1 probe, which was the first human-made object to enter interstellar space and has been hurtling through it at 35,000 miles per hour for more than 40 years. That's fantastic, except that it'll take another 40,000 years to travel the average distance between stars. Since the galaxy is more than 100,000 light-years big, most interstellar distances would take longer than a human lifetime to travel if you were moving slower than light. It will appear that a galactic-spanning human civilization is impossibly unlikely if the known laws of physics are valid, except of course if you manage to construct a warp drive. Scientists have at last cracked the code, making the concept a working reality. Is there such a thing as warp drive, and what exactly is it? How near are we to actually going to other stars? There is no question that mankind will never be able to fully explore the universe. The Proxima Centauri star, which is the closest one to Earth, is over 4 light-years away. For a human to make the same journey, it would take tens of thousands of years, even with the finest propulsion technology currently in use. However, it might be possible to shorten the distance traveled. There are numerous methods for doing that, ranging from nuclear propulsion to laser-accelerated solar sails, but even with the help of these technologies, a human cannot make this journey in one lifetime. Only those who can travel at the speed of light or faster can actually access the galaxy. Because of this, theoretical physicists have long considered the ideal propulsion system a bubble in space and time that would allow a spaceship to quickly travel between stars, much like the USS Enterprise did. This is a cutting-edge scientific investigation that has been liberally sprinkled with optimism. Since the first episode of the science fiction television series Star Trek was broadcast, viewers have had countless unanswered questions. In recent decades, the science fiction series has always been entwined with actual science. Warp drive was only one of several forward-thinking concepts featured in the series that captivated viewers all across the world. It was the original concept behind Star Trek's ability to warp through space at the speed of light, therefore challenging Einstein's theory of relativity, which forbids any object from outrunning the speed of light. Since nothing can move faster than the speed of light, Einstein's theory of relativity throws a wrench into the works. A common consequence of increased velocity is an increase in mass. It becomes more challenging to accelerate a heavy object. In a nutshell, traveling at the speed of light is impossible. What about with a warp drive? Warp drive is often considered the ultimate goal of space travel. It has been theorized to have a propulsion system capable of speeds greater than light. Do you not agree that this will allow mankind to travel to any part of the galaxy at any time? Taking into account Einstein's theory of relativity, it appears to be next to impossible to undermine the idea. Will it though? Can warp drive even be achieved? To begin, let's focus on the warping aspect of a warp drive. Certainly in Albert Einstein's general relativity, space and time are portrayed as a four-dimensional fabric that can be folded, twisted and stretched. Space-time ripples or gravity waves have been detected for the first time. This means that space-time can be distorted. The warping component of a warp drive often entails changing spacetime's curvature in order to bring two distant locations closer together and then allow you to jump between them. Long before Star Trek popularized the term warp drive, this was a fundamental concept in science fiction. But up until 1994, there was no science to support it. In that same year, Miguel Alcubierre devised a solution to the fundamental general relativity equations that showed how an area might compress spacetime in front of it and expand spacetime behind it to produce a traveling warp bubble. This was excellent news for warp drive enthusiasts. It may be feasible to exceed the speed limit for all objects by breaking the rules of physics. The Alcubierre warp drive notion was put forth at this point. It might be conceivable for the Alcubierre warp drive to go around the speed of light by warping spacetime, just like in the television series Star Trek, rather than exceeding it. The hypothesis predicts that the spaceship will be located inside the warp bubble, surrounded by a negative mass ring. As the spaceship travels through the ring of negative mass, the area of space in front of it will contract while the area behind it will expand. By doing this, the spaceship will be able to move at 10 times the speed of light within the bubble. However, the spaceship will continue to obey the universal speed limit while general relativity continues to hold. Albert Einstein's theory of relativity has two elements according to physicists. The 1905 special theory of relativity describes the behavior of things moving at the speed of light. Einstein generalized these concepts for moving bodies 10 years later. The three spatial dimensions we are familiar with up, down, left, right, and front, back are inextricably linked to time according to general relativity, which mass causes this spacetime to distort. Albert Einstein's theory of relativity has two elements according to physicists. The 1905 special theory of relativity describes the behavior of things moving at the speed of light. Einstein generalized these concepts for moving bodies 10 years later. The three spatial dimensions we are familiar with up, down, left, right, and front, back are inextricably linked to time according to general relativity. Each mass causes this spacetime to distort. The seminal work of Albert Einstein postulated that our universe consists of four dimensions of spacetime. Nothing in spacetime is fixed. When heavy things are placed on it, it wrinkles like a tablecloth. Light speed limit applies to everything that travels across the tablecloth or across spacetime. However, the tablecloth itself can be bent at any rate, as evidenced by the cosmos itself. In certain circumstances, the original spacetime structure, for instance, is thought to have extended briefly at time of the Big Bang, and it did so considerably more quickly than any ray of light could. Galaxies that are exceedingly far away from us are still being accelerated by the expansion past the speed of light, making it impossible for their light to reach us. Alcubierre estimated that it would only be a short step to a warp drive based on his discovery. One could reach their destination at a speed faster than light if spacetime were to be compressed in front of a spaceship and expanded behind it to make up for it. The crew would not be aware of the length of the interstellar travel because the ship would continue to be enclosed in a bubble. Alcubierre likened it to riding on an airport passenger conveyor belt in a 2017 lecture, saying you can imagine that the floor behind you is being created out of nothing and in front of you it is being destroyed, so you move along. However, expressing this concept in terms of general relativity immediately raises significant real-world issues. First, you would need to pack a massive mass inside a bubble with a wall thinner than an atomic nucleus in order to distort spacetime so drastically. The bubble would then require two different types of materials to be stable. The area in front of the bubble would close due to the gravity of ordinary mass propelling the entire structure forward. However, the area behind the bubble would also need to grow much like rising bread dough. Alcubierre asserted that you would require some kind of negative energy emanating an antigravity to cause that expansion. That is the drawback of negative energy. Most scientists' minds were closed at that point. According to Einstein's formula, E equals mc squared, energy is equal to mass without any constraints, hence it stands to reason that energy must be positive. However, it is possible for it to be negative in quantum theory. However, this only appears happen in extremely unusual circumstances. It's hard to imagine a practical application for the so-called Casimir effect because the amounts involved are so small. This is a point acknowledged by Alcubierre, a physics professor at Mexico's National Autonomous University. Warp drives are greatly lacking, he and one of his colleagues noted in a recent preprint study. His focus has shifted to established phenomena like black holes. However, the idea of a warp drive still intrigues many people, especially Trek fans and the rare gravitational physicist who publishes a new take on the topic. The overall mass required to bend spacetime is demonstrated to be less than that of our Sun in some of these articles, demonstrating how the bubble's mass requirements might be reduced. The issue of negative energy had eluded everyone until Eric Lentz took it up in the Göttingen lockdown. Lentz, trapped in his lab, figured out how to build a warp bubble with only positive energy. He may have just solved the biggest problem with warp drives. It was made feasible by a unique aspect of the geometry of spacetime that Lentz found hidden within Einstein's field equations. More specifically, within the general theory of relativity, these equations can determine the amount of spacetime distortion caused by a specific distribution of matter and energy. They can also be used by researchers to calculate the mass and energy required to produce a particular curvature of space, as Alcubierre did. But it is very difficult to deal with a dynamic four-dimensional entity like spacetime. When written out in their entirety, Einstein's formulas result in a complex web of nested differential equations with thousands of elements. You only consider some of those concepts depending on the assumptions you make about a specific physical circumstance. It provides theorists with a nearly endless playground. Lentz explicitly looked at the presumptions used in Alcubierre's work to arrive at the negative energy needs. Lentz started by studying spacetime, modeling the multidimensional substance as a stack of extremely thin layers. Just as his colleague Alcubierre had only taken into account relatively straightforward linear correlations between the equations for transferring one layer onto the next, he discovered choosing more intricate hyperbolic relations at this point, which often express quickly changing values, yields a different warp bubble than the one Alcubierre got. Lentz's calculations show that it still requires a tremendous amount of mass and energy, but only in the positive sense. The bubble Lentz created in 1994 differs in appearance from Alcubierre's. It is made up of flocks of diamond-shaped areas of distorted spacetime. A complex layering of rings and disks composed of an incredibly dense fluid of charged particles akin to the substance found inside neutron stars would be required to construct such a spacetime geometry in reality. Thus, the application of technology is still very, very distant from enabling near-light speed flight. But now that Lentz's most recent work indicates that no strange negative energy densities are required, the theoretical games are within the bounds of known physics. Some scientists claim that all that is required to create a warp bubble is a properly sized shell composed of dense material that bends spacetime nearby while leaving the universe it travels through and the space inside the shell relatively unaltered. When one went away from the shell's wall, the gravitational field did not instantly vanish, instead it would deteriorate over time. Therefore, inside the bubble, spacetime would also be bent. This phenomenon would be most apparent to those in a spaceship in the center of the bubble, as time would pass more slowly for them than it would for everyone else in space, because according to the theory of relativity, time is impacted by gravity. Perhaps interplanetary travelers enjoy the slower pace of time on a spacecraft. All previous theories merely presuppose that the spacetime bending is already moving quickly. Light travels at a speed of 299,000 kilometers per second. This is a physical constant. According to Einstein's special theory of relativity, the fastest any particle can go is the speed of light, and it can only accomplish this if it has no mass. As a result, there is no way to accelerate objects faster than the speed of light according to current physics. However, on closer investigation, this restriction only holds true for the universe's four-dimensional spacetime. Beyond that, even higher speeds seem conceivable. None of the physically conceivable warp drives can accelerate to speeds faster than light, claims Balbrick. The reason for this is that you would need matter that could be ejected at velocities faster than light, yet no known particle can do so. Additionally, because of the incredibly intense curvature of space around them, the spaceship's crew would lose contact with the outside world if they attempted to manipulate the bubble. Lentz agrees that these concerns are a problem, but he thinks a way to overcome them can be found. Meanwhile, some scientists claim that it is also feasible to travel to faraway stars at a speed of a third or even a half of the speed of light, particularly if time moves more slowly for those inside the warp bubble. Just don't consider the possibility that by the time you return, all of your relatives who were still on Earth will have likely passed away from old age. But at least the notion has become less absurd. Whether or not warp bubbles can actually function without negative energy is still up for discussion. 3 theorists recently argued that this assertion was true only for observers traveling in close proximity to the bubble. Additionally, not everything that is predicted by the theory of relativity is real or technically viable. Einstein's field equations, for instance, can be used to support unusual spacetime changes that have never been seen, such as Einstein-Rosen-Bridges white-hole, which are the antithesis of their black hole counterparts and wormholes. That might be because such events are prohibited by undiscovered natural principles. Therefore, some researchers advise against engaging in excessive fantasies. Martin Tajmar, a specialist in space propulsion at the Technical University of Dresden, for instance, believes that the work being done on warp drives has no immediate use. He claims that the enormous quantities required are simply beyond what can be tested on Earth. Almost all seasoned warp drive researchers concur. They view their study more as a means of discovering the boundaries of relativity than as a means of preparing for actual investigations, according to Lobo. Even hypothetical thought experiments can be helpful in this attempt. On the other hand, Lentz is actively attempting to put his theory into practice. Following his research in Göttingen, he accepted a position with an I.T. firm. However, in his spare time, he continues to consider ways to boost a bend in spacetime to speeds faster than light, while also lowering the amount of energy needed to do it. Although significant, there is still a long way to go before warp speed and interplanetary travel are commonplace. However, thanks to technological breakthroughs, the solutions we seek might be within reach. Thanks for watching another episode of Voyager. While you're still here, make sure to click the video on your screen for more mind-blowing videos about space.